So the proof by contradiction revolves around the concept of the converse of a statement. So the converse of a statement is the set of all possibilities that would lead to that statement being false. So take, for example, the statement, all sheep are white. The converse of that statement. Now, you'd be forgiven for thinking that it's all sheep are not white, but that's a much stronger statement than the converse. The converse of that, the set of all statements that would prove that false, is the statement not all sheep are white, not that all sheep are not white, because all we need to find is all sheep in the world could be white, except one. All we have to do is find that one black, pink, green, whatever colour it is, sheep, and that disproves the statement that all sheep are white. So the converse is not all sheep are white. Or an equivalent statement, and more helpful, and this is the best way to write it: there exists at least one sheep that is not white. So that there is the equivalent of the statement above, but this here is the most helpful way that we can write it for in terms of proof by contradiction. So not all sheep are white is the equivalent of saying there exists at least one sheep that is not white. So proof by contradiction involves, basically, if we're asked to prove something, we assume that the converse is true, i.e. the exact opposite, and do some maths with the exact opposite until it breaks down. So we prove the exact opposite to be false. If we prove the exact opposite to be false, then that means that the opposite of that must be true. So let's do an example. Actually, I'll write down first proof by contradiction is proof in which we disprove the opposite of what we want. Disproving the opposite of what we want. So let's do an example. E.g., prove by contradiction that an odd number squared is always odd. And these are the set of steps every time that we're going to have to go through. So step 1, and there's often a mark for this in an exam, assume the converse of what we're trying to prove is true. So in this case, the converse assume there is at least one odd number to n plus 1, where n has to be an integer. One odd number, 2n plus 1, such that that number squared is even. So the statement we're trying to prove is that every time we square an odd number, we get another odd number. So what we're going to do, we're going to assume the converse of that. We're going to assume that there exists at least one odd number, such that when we square it, disproves that statement. That's the converse. At least one case that disproves it. Because I've claimed every single odd number squared is also odd. All I need to do is find one example to disprove it, and that's what I'm assuming happens here. I'm assuming there's one or more examples that'll disprove that statement. So often that's a mark in an exam for what I've just written there. Then step 2. We manipulate it algebraically until a contradiction or inconsistency occurs. So we're looking for a nonsense statement. So let's square it. 2n plus 1 squared equals 4n squared plus 4n plus 1. And we're trying to now prove that that's even though we know that's false. Even though we know that really it's odd, and that's what we're being asked to prove. We're going to try and prove the converse, that actually it's even. So the best way to prove that something's even is to take out a factor of 2 from every term that we can. 2n squared plus 2n, and I've ran out of things that I can take a factor of 2 out of, with a plus 1 on the outside. So what we're trying to do here, try to prove this is even though we know it's false. I think that's the only time in my life actually that I've ever used the word even twice in a grammatically correct sentence next to each other. It's the little things in life. Try to prove this is even though we know this to be false. And clearly, it's odd, which is of the form 2k plus 1, therefore odd. We assumed it's even. We put ourselves out there, scream from the rooftops that we're trying to prove that this is even, and we failed. We didn't just fail, we showed that we were exactly wrong in trying to prove that it was even. So if it's not even, if there doesn't exist at least one even number, or rather one odd number that squares to make an even number, then the opposite of that, i.e. the original statement, must be true. So an odd number squared is always odd. We assumed the opposite, disproved it. Disproving the opposite is the equivalent of proving the original statement. So step 3, state the contradiction. Then conclude. So this contradicts the assumption that there exists, and don't get lazy with how much you write out here, actually state it explicitly. This contradicts the assumption that there exists at least one odd number such that its square is even. So we disproved the possibility that there even exists an odd number whose square is even. That means that all square odd numbers must be odd. Therefore, the square of all odd numbers is odd. And there's many other different styles of proof that you can go through to prove that the square of an odd number is odd. I needn't have done this by contradiction. I needn't have gone through the hassle of assuming the opposite to be true. We could have just went straight in for the kill and done that there. However, I just want to start with an easy example of why how proof by contradiction can be used. So any statement you make must have the word contradicts in, and you must also say what it contradicts, and you also must conclude. So this here is a key word. Contradicts or contradiction must be in there. So it must use this word. Let's try another. E.g., prove by contradiction that there is no greatest even integer. Prove by contradiction that there is no greatest even integer. So I'll give you half a minute to write down the converse of that statement. So assume that there exists a greatest even integer to n. Now you might have wrote, based on what I said before, assume that there exists at least one greatest even integer to n. That's also technically right, but there can't be more than one greatest even integer, which is why I've slightly modified this statement. So technically, if you said assume there is at least one, that, as I say, that's technically right because 1 is at least 1. But actually, I've narrowed down the statement here. So assume that there exists a greatest even integer, 2n. Consider, so we're trying now to disprove that statement. 2n plus 2. Actually, I'm going to tighten the statement up here, where n is an integer. Probably not required in the exam, but certainly required to make the statement correct. Consider 2n plus 2, which is equal to 2, lots of n plus 1, which is a greater even integer. This contradicts the assumption that 2n is the greatest even integer, therefore there does not exist, or rather there is no greatest even integer. Done. Let's do another. E.g., prove by contradiction that if n cubed is even, then n must also be even. So take 30 seconds to write down the converse of that statement. Assume the opposite. Then we're going to do some maths until it appears that our statement was nonsense. So the converse of that statement, assume that there exists at least one odd number, n equals 2m plus 1, such that n cubed is even. I'm going to try and find that number now. So go for it. Try and prove something we know to be wrong. Try and prove 2m plus 1 cubed is even, and miserably fail at it, which is what we want. So we're saying in every single case, in the initial line here, the question's saying that every n, when cubed, must be even. We're saying, well, let's pretend we can find a single or more case where if we cube an odd number, we get an even number. So we can do a triple bracket multiplication, or we can do the binomial expansion. I prefer the binomial expansion. Like that. Equals 8m cubed plus, so 3, I do this as you should on the calculator, 3c2 times 2 squared times 1 is 12. M squared. 3c1 times 2 to the power of 1 is 6. M and plus 1. Double check my 3c2 answer. Yeah, 12. So we've got that there. And let's try and prove that that's even by taking out a factor of 2. So we've got 4m cubed plus 6m squared plus 3m. And we failed miserably, which is what we wanted. There's a 1 that we can't factorise a 2 out of. Which is of the form 2k plus 1, therefore odd. This contradicts so much like hypothesis testing in maths, it's important what you write here. The word contradicts or some variant, contradiction, of that word is necessary. This contradicts our assumption that there exists at least one odd number n such that n cubed is even. Therefore, if n cubed is even, n must also be even. Now there's a few standard proofs here that you need to know in proof by contradiction. 2 in particular. So first of all, what I want to do is define what rational and irrational numbers are. Rational and irrational numbers. So a number is rational if it can be written as a fraction only involving integers, and the set of all rational numbers, and you probably don't need to know this for the syllabus, we denote by Q. And it's the set of all numbers formed by a fraction such that A and B are integers. If it can't be written like that, then it's not rational. If it can be written like that, then it is rational. So any fraction of integers is rational, and actually comes from the word ratio. If it can be written as a ratio of integers. So, without wanting to patronise you, but I suspect I'm about to, 2/3 is a fraction of integers, therefore it is rational. Root 16 is rational because it can be written as 4/1. Root 3 isn't rational because it can't be written as a fraction of integers. You need that root sign in order to write the value of root 3. So yes, yes, no. Pi as well. Pi isn't rational. It can't be written as a fraction of integers. And just a quick note. Any number, and you probably know this already, any number that is not rational is called irrational. Any number not being rational is irrational. So let's do, before I go on to the standard proofs, actually, there's an example I want to do, e.g. prove that the sum of two rational numbers is also rational. I should really, thinking about it, specify prove by contradiction, because there's other ways of proving it. Prove by contradiction is the way we're going to do it. So prove by contradiction that the sum of two rational numbers is also rational. So what we're going to do, first of all, do the assumption. Assume that there exists at least one pair of rational numbers x equals a over b, y equals c over d, where a, b, c and d are integers. That's what makes it rational. Such that the sum of these two numbers is irrational. Okay, so add them together. Add those two numbers together. And it would be helpful to write them as a combined fraction. So you can take a minute to do that. Okay, so adding them together, x plus y equals a over b plus c over d equals ad plus cb over bd. Now we've assumed that that's rational, so we've got to basically spell out why that statement's nonsense. So basically state why the top of that's an integer and the bottom of that's an integer. So a and d are integers. Therefore, so is AD. And I'm probably going a bit overboard here, but I'm guaranteeing us the marks. C and B are integers. Therefore, so is CB. And if we add two integers together, that implies that AD plus CB is also an integer. Okay. BD are integers. As I say, I'm probably going way overboard here. Therefore, so is BD. So, numerator is an integer. Denominator is an integer. Therefore, x plus y is rational. So the top's an integer, the bottom's an integer, and a fraction of integers is rational. Leads to a fraction where the top's an integer, the bottom's an integer, and that's the definition of a rational number. Right, so some standard proofs that you need to know, and there's two of them. E.g., prove by contradiction that root 2 is irrational. And this one's ever so slightly different than the proofs we've done so far. So what we're going to do here is assume and there's two parts to this, actually. I should have spelled out. I'll spell out a bit better the stages. So stage 1, what we need to do, lay some groundwork, prove that if n squared is even, so is n. So we're not going to get onto the good stuff, the actual proof of root 2 being irrational, until we've done this. So we've done that for n cubed. Have a look back up at your notes for proving that for n cubed. And follow the same process to prove that if n squared is even, then so is n. Okay, so the first stage, put that in red actually, as I do with most of my instructions. So assume there exists at least one odd number to n plus 1 such that 2n plus 1 squared is even. So let's go and try and disprove that. So here's our number, 2m plus 1 squared equals 4m squared plus 4m plus 1. and try and take out a factor of 2 to get 2m squared plus 2m plus 1, which is of the form 2k plus 1. By the way, I'm going to go back up here and tighten up this statement and specify that m must be an integer. Not necessary for the marks, but certainly necessary to make it right. Which is the form of the form 2k plus 1, therefore odd. This contradicts our assumption that (2m plus 1) squared can be odd, can be even. Therefore, the square of an even number go back up to this statement here. If n squared is even, then so is n, is what we were trying to prove. Right, stage 2. Going in for the kill. Actually get on to proving the thing about root 2 now. Stage 2. Use the above in proving root 2 is irrational. Right, okay, so what we're going to do, we're going to assume the converse. So, assume root 2 is rational, and so can be written as a over b, where a and b are integers. And this is the key point here, which we haven't seen before. A and b are integers with no common factors. I.e., a fraction of integers. I'll put this in red because this bit I'm about to write is explanation rather than being necessary for the marks. I.e., a fraction of integers written in its lowest terms. That's when a and b have no common factors. It's a fraction in its lowest terms. So for example, 6 over 8 isn't in that form because 6 and 8 have a common factor 2. We can write that in its lowest terms, i.e. two numbers with no common factors other than 1. Like that. So a fraction of integers written in its lowest terms. Like that. Tidy that up a little bit. Okay, so we're going to do some maths now to try and prove that that statement is nonsense. But here, what we're trying to disprove is this bit here, the no common factors part. Trying to disprove this. And as I say, this is just a proof that you've got to learn. So we're assuming root 2 can be written as a over b, where a and b are integers. If we square both sides, we get 2 equals a squared over b squared times both sides by b squared, which means that b squared, or rather 2b squared, equals a squared. So a squared is 2 times something. So if a squared is 2 times something, then that must be even. Therefore, a squared is even. Since 2 times an integer. So we've got a is even. If a is even, it can be written as 2m, where m is an integer. So letting a equals 2m now, this means that a squared equals 2b squared becomes 2m squared equals 2b squared, like that. Which means that 4m squared equals 2b squared, which means that b squared equals 2m squared, and b squared is even. So we've got a squared and b squared are even. Hopefully you're convinced by that, because they're both 2 times an integer. And now we're going to go back up to the work we did before. Prove that if n squared is even, so is n. So we're going to use that fact now. If an integer squared is even, then so is the original integer. Therefore, if a squared and b squared are even, then so are a and b, by the stage 1 proof. Therefore, if a and b are both even, and this is where we've just disproved the bit I highlighted before, then they share a common factor 2. We assumed they didn't have any common factors. If a and b are both even, then they share a common factor 2. This contradicts our assumption that root 2 can be written as a fraction a over b, where a and b are integers, where a and b have no common factors. Therefore, root 2 is irrational. So quite a strange proof. So going back over, reviewing it, stage 1 was imperative in making the conclusion, proving that if n squared is even, then so is n. Then we used that. We showed that if root 2 can be written as that, which it can't by the way, but if root 2 can be written like that, then a squared has to be even, b squared has to be even, therefore a and b both have to be even, contradicting the no common factors assumption. So proof that root 2 is irrational. You might be asked to do that for other integers, but learning that style of proof is imperative, so keep looking over it. One last proof I want to go through before we finish. E.g., and it's another one, prove that there is no greatest prime number using proof by contradiction. Okay, so first of all, assume there is a finite list of primes. We know there's not. We know that prime numbers are infinite. Assume there is a finite list of primes. Prime 1, prime 2, all the way up to the final prime, Pn, prime n. Consider the product P1 times P2 times all the way up to Pn times all those primes together, then add 1. Any prime number, or any number for that matter, can be written, as you know from GCSE, as the product of prime factors. That's the fact we're going to use. Any number can be written as the product of prime factors. So, at least one of our list of primes, P1, P2, all the way up to the final prime, must be a factor of our number P1 times P2 times all the way up to the final prime plus 1. That statement we know to be true. We know that every number can be written as the product of prime factors. So our newly constructed number, P1, P2, P3, P4, P5, all the way up to Pn, then add 1, has to have at least one prime factor. So if we divide this number by P1 or P2 or any of those up to Pn, we can see that it's going to be a factor of this part here. It's going to divide by this part, but it's always going to leave a remainder of 1. It will leave a remainder of 1. But we know this statement to be true. We know that every single number ever can be written as the product of prime factors, well, apart from 1, that is. Therefore, there has to exist another prime number that divides this, i.e. itself. So, if it always leaves a remainder, no matter what number we divide by, therefore, P1, P2, I should put the times signs in actually, P1 times P2 times plus 1 must itself be prime. None of the previous primes divide it. So because every number can be written as the product of primes, this itself must be prime, as no previous prime numbers divide it. Therefore, this contradicts our assumption that Pn was the greatest prime. We assume that there was a list of primes where Pn was the greatest. That's contradicted that assumption. Therefore, there does not exist a greatest prime number. So those two last proofs there, you've got to learn those. Those could come up in an exam. Often they come up in the context of spot the error in the proof questions. So I'll bid you farewell and good day. Hope you found that useful, and I will see you next week.